Right, so here's what I've just been saying. So p squared plus p is less than p plus 1 all squared. Now the second condition of your pumping lemma says that the size of y is positive. Right? It's not 0 or negative, it's a positive. So the sign of y, the size of y is greater than 0. Right? In other words, it's not the empty string. Therefore, well, I don't even see it. Now, the size of xy squared z is equal to the size of xyz plus the size of y. Right? We did that towards the bottom of the previous session. Okay, so that means that the size of y squared z is greater than the size of xyz. Right? I'll say that again. The size of xy squared z equals the size of xyz plus the size of y. But the size of y is positive, right? It's not 0. So this then is strictly larger than the size of xyz. Follow that? Okay. Right. So that means now what is the size of xyz? Well, it's p squared, right? Because that's s, and s is a member of your language D, so it's a perfect square. So if this is greater than that, that means that the size of xy squared z is greater than p squared. Right? That's what you've got here. Right? So yeah, so the length of, oops, that shouldn't be there. So the length of this string is greater than p squared. And from here, this analysis, we've also got, so the size of xy squared z is greater than p squared. Okay? But we've also got from here, let's see, the last line in the previous session, we had the size of xy squared z is less or equal to p squared plus p. But p squared plus p is less than, strictly less than, p plus 1 all squared. Therefore, the size of, well, therefore the size of xy squared z is strictly less than p plus 1 all squared. Right? Now bring these two together. You've got this inequality and you've got this inequality. Now this one says that the size of xy squared z is greater, strictly greater than p squared, so it's larger than a perfect square, right? And here, the second inequality, you've got the size of xy squared z is less than p plus 1 all squared, so it's strictly less than the next perfect square. In other words, xy squared z, its length lies strictly between two perfect squares, between p squared and p plus 1 all squared. Okay? So the value, the size of this is lies between, strictly between, two perfect squares. In other words, it is not, the size of this is not a perfect square. And since we're talking about a unary language, that means that xy squared z is not a perfect square. It doesn't have a perfect square number of ones in it. Okay, and therefore we've found a string, 1 to the p squared. That was our s from in the previous session. Okay, so this cannot be a perfect square. So we've got a contradiction. So this pumped this pumped S, by having an extra Y in it, does not belong to S. But that's a contradiction in the pumping lemma. You know, the pumping lemma says it has to belong to S. You know, the pumped string must belong to the language if the language is regular. Well, it doesn't belong. This one here, the string, the pumped string x y squared z, does not belong to the language D. Therefore, you've got a contradiction. So by modus tollens, you know, in the proof of contradiction, you have shown, therefore, that what's the language? D. Therefore, language D is not regular. So you've proved it. Okay, so D is not regular. All right. Now the final example. It's a bit of a trick. Instead of pumping up, like increasing the number of Y's here, you know, pumping, like you're putting more air into a tyre, and when you do that, the tyre sort of grows bigger. Or and here you're increasing the length of your string. You've probably seen those balloons. When you blow into them, they sort of get longer. So you're pumping the balloon in a sense. So in a sense, pumping a string, just making it longer by adding more and more copies of the Y. Okay. Well, now pumping down is like going the other way, having less copies of Y in your string. Now, since your original string S is of the form x, y, z, according to the pumping lemma, to pump down would just, I mean, there's only one copy of Y, right? But the number of copies of Y, according to the lemma, can be 0, right? According to the pumping lemma, the string, the pumped string, x, y to the I, to the power I, z, belongs to the language also. But the I, you know, the power of I, the I can be 0, right? So I is greater or equal to 0. So in this case, when we pump down, we're going to decrease the number of Y's, you know, the Y substring, in your pumped string. We'll go the other way. We'll go down instead of up. So your original string S, that is x, y, z, that will now get shrunk to just xz, right? Because the y is now to a power 0. That's the empty string. So you're just left with xz, right? So that's pumping down, and we'll show using that idea, pumping down, to show that a particular language is not regular. Okay, that's sort of the idea. This new notion of pumping down. Okay, now the language, I call it E now. It's a binary alphabet, you know, 0 or 1. Here's the language. So here are your strings. They are of the form all all the zeros in this string clumped together on the left hand side, and all the ones in the string on the right hand side. But the number of zeros is greater, strictly greater, than the number of ones. Okay, so E is a set of all those strings satisfying that property. Okay, and as usual, you know, this is like the 5th time we're doing this now. We're going to use the pumping lemma to prove that this language is not regular, and again using proof by contradiction. So that pattern has been the same throughout these 5 examples, you know, using proof by contradiction via use of the pumping lemma, right? And let's see, so as usual, you know, by contradiction, so we assume the opposite of what we're trying to prove. We're trying to prove that E is not regular, so the opposite of that is that it's not regular, therefore it's regular. So assume E is regular, let little p be the pumping length as usual, okay? And Now here's, as usual, the critical part, the choice of your string that you're trying to show when it is pumped, in this case pumped down, that it does not belong to the language E. Okay? So here's what Sipser gives. So he says take this candidate string that we hope will enable us to come to a contradiction, a counterexample. So let the string S be have 0 to the p plus 1 and then 1 to the p. Okay, so there is one more 0 than the number of zeros is one more than the number of ones. Okay, in this string. So this string S satisfies this definition. Okay? So S belongs to this alphabet, to this language. You know, belongs to E. Okay, because it satisfies. You know, p plus 1 is obviously larger than p. So so that's true. Okay, this is true. So it belongs to the language E. E is assumed to be regular, and therefore, what else? The size of S, is it larger than? Well, what is the size of S? This given this string. Well, it's 2p plus 1. That's pretty obvious, right? Well, 2p plus 1 is obviously larger than p. So the size of this string is larger than the pumping length. And so therefore the string S can be split into 3 substrings, you know, via the pumping lemma XYZ, as usual, right? And again, our famous condition 3. Here's here I was mentioning. Condition 3 implies that the Y here can consist only of zeros. Now, to Sipser that was obvious because he didn't say anything about why that's the case. Now it struck me that it wasn't so blindly obvious that it did not demand any discussion.